In Part 7 of Lecture 1, we will discuss symmetric multiprocessors. A symmetric multiprocessor can be defined as a standalone computer system with the following characteristics. There are two or more similar processors of comparable capability. These processors share the same memory and I/O facilities and are interconnected by a bus or other internal connection scheme, such that memory access time is approximately the same for each processor. All processors share access to input-output devices, either through the same channels or through different channels that provide paths to the same device. All processors can perform the same functions, hence the term symmetric. The system is controlled by an integrated operating system that provides interaction between processors and their programs at the job, task, file, and data element levels. The first 4 points should be self-explanatory. The last one illustrates one of the contrasts with a loosely coupled multiprocessing system, such as a cluster. In the latter, the physical unit of interaction is usually a message or complete file. In an SMP, individual data elements can constitute the level of interaction, and there can be a high degree of cooperation between processes. An SMP organization has a number of potential advantages over a uniprocessor organization, including the following. In performance, if the work to be done by a computer can be organized so that some portions of the work can be done in parallel, then a system with multiple processors will yield greater performance than one with a single processor of the same type. Availability. In a symmetric multiprocessor, because all processors can perform the same functions, the failure of a single processor does not halt the machine. Instead, the system can continue to function at reduced performance. Incremental growth. A user can enhance the performance of a system by adding an additional processor. Scaling. Vendors can offer a range of products with different price and performance characteristics based on the number of processors configured in the system. It is important to note that these are potential rather than guaranteed benefits. The operating system must provide tools and functions to exploit the parallelism in an SMP system. An attractive feature of an SMP is that the existence of multiple processors is transparent to the user. The operating system takes care of scheduling of tasks on individual processors and of synchronization among processors. The figure illustrates the general organization of an SMP. There are multiple processors, each of which contains its own control unit, arithmetic logic unit, and registers. Each processor has access to a shared main memory and the I/O devices through some form of interconnection mechanism. A shared bus is a common facility. The processors can communicate with each other through memory, messages and status information left in shared address spaces. It may also be possible for processors to exchange signals directly. The memory is often organized so that multiple simultaneous accesses to separate blocks of memory are possible. In modern computers, processors generally have at least one level of cache memory that is private to the processor. This use of cache introduces some new design considerations. Because each local cache contains an image of a portion of main memory, if a word is altered in one cache, it could conceivably invalidate a word in another cache. To prevent this, the other processors must be alerted that an update has taken place. This process is known as the cache coherence problem and is typically addressed in hardware rather than by the operating system. A multi-core computer, also known as a chip multiprocessor, combines two or more processors called cores on a single piece of silicon called a die. Typically, each core consists of all of the components of an independent processor, such as registers, ALU, pipeline hardware, and control unit, plus L1 instruction and data caches. In addition to the multiple cores, contemporary multi-core chips also include L2 cache and, in some cases, L3 cache. The motivation for the development of multi-core computers can be summed up as follows. For decades, microprocessor systems have experienced a steady, usually exponential increase in performance. This is partly due to hardware trends, such as an increase in clock frequency and the ability to put cache memory closer to the processor because of the increasing miniaturization of microcomputer components. Performance has also been improved by the increased complexity of processor design to exploit parallelism in instruction execution and memory access. In brief, designers have come up against practical limits in the ability to achieve greater performance by means of more complex processors. Designers have found that the best way to improve performance to take advantage of advances in hardware is to put multiple processors and a substantial amount of cache memory on a single chip. A detailed discussion of the rationale for this trend is beyond the scope of this course. An example of a multi-core system is the Intel Core i7-5960X, which includes 6 x86 processors, each with a dedicated L2 cache and with a shared L3 cache, as seen in the upper figure. One mechanism Intel uses to make its caches more effective is prefetching, in which the hardware examines memory access patterns and attempts to fill the caches speculatively with data that's likely to be requested soon. The lower figure shows the physical layout of the 5960 in its chip. The Core i7-5960X chip supports two forms of external communications to other chips. The DDR4 memory controller brings the memory controller for the DDR double data rate main memory onto the chip. The interface supports 4 channels that are 8 bytes wide for a total bus width of 256 bits, for an aggregate data transfer rate of up to 64 gigabytes per second. With the memory controller on the chip, the front-side bus is eliminated. The PCI Express is a peripheral bus. It enables high-speed communications among connected processor chips. The PCI Express link operates at 8 gigatransfers per second. At 40 bits per transfer, that adds up to 40 gigabytes per second.